So I had unmuted already, but we're starting the recording now. So if you need to take the October test, the registration deadline Manoj just said was in 2 days by the end of this month, which is September 30th. So 2 warm-up problems to start. So first one is just simple computing with roots. So, first one, I'm not sure how well that is going. I'm fighting the glare a little bit. So it says, what is the square root of 24 plus the square root of 150? And the second says, if n is a positive integer, which expression must be an odd integer? And 3 to the n power, n to the third power, 3 times n divided by 3, or 3 plus n. Give you a couple minutes and then we'll dive in the meat of the day. Go ahead and raise your hand online if you're done. So there's an old joke that talks about an engineer, a physicist, and a mathematician discovering that their hotel rooms are on fire. The engineer will see the sink and go to the sink and just get water and throw it at the fire. The physicist will calculate exactly how much water is needed and put out the fire. And the mathematician will say, there's an answer, and go back to sleep. And so even more so than the answer, because the answer in this problem is not the answer on our actual test, we are interested in the path to the answer. So from online, what is the key to being able to solve this problem? What do we need to do in order to get to the answer?
I think it's I forgot the term, but it was to find the perfect root, I believe.
So you're looking for the roots, but what you want is to get it into like term, which is what your brain was thinking of. We want to pull out any perfect squares so that we can get them into a form that they are like terms. Because right now they're very different, but what is a perfect square that we can pull out of 24?
4.
4. And so we have 4 and 6. 4 is a perfect square, and this becomes 2 square roots of 6. What is the perfect square we can pull out of 150?
25.
25. And again, there's that 6. 25 is a perfect square, and the square root of 6 stays behind, and so now we have 2 square roots of 6 and 5 square roots of 6. We have 7 square roots of 6. And so being able to realize, oh, we need to reduce this root or simplify the radical and get it into a form that they match, then you can find your answer. But that being able to say this is what to do, that is more important than 7 square roots of 6, because 7 square roots of 6, that's not what we want on the test. We just need the process. We need the ability to do that. And so along the same lines, this is one that it doesn't fit nicely into any of the categories except what I call number sense. This ability to recognize how numbers behave is a huge thing. And in the shift to the new test, I'm noticing more and more number sense problems. So what does it take in order to be an odd integer? What do we need in order to get an odd answer every single time? So here's a sampling of integers. They happen to all be positive. Maybe I'll throw some negatives on there. Under addition, if we add any number, will it always be odd? Or if, for instance, we take 3 plus 7, does that give us an odd number? No. And so adding 3 to any number doesn't guarantee that we've got an odd one. Dividing by 3, well, if we take 4 divided by 3, we're not even in integer territory anymore. We're ending up with fractions. How about multiplying by 3? If we take 3 times 3, that's 9, that's odd. If we take negative 5 times 3, that's negative 15, that's odd. But if we take 6 times 3, what are we ending up with? 18, still even. So the only way to get an odd number every single time is to only multiply odd numbers. The instant you multiply by any even number, it's going to be even because you have an even number of times. And so if you were to take 4 to the third power, 4 times 4 times 4, still even. The only way is to multiply an odd number, in this case 3, no matter how many times, it's going to stay odd because it's never going to be a multiple of 2. It's never going to be divisible by 2. That one would only be divisible by 3. And so understanding how those numbers behave, if you've got that foundation, great. If you could do that without running test cases, that's fine. But if you are not confident with that, you need to consider both positive and negative numbers in your test case. You've got to consider both halves. And so if you do not know off the bat, oh, this is what's going on, if you don't understand that, if you're running test numbers, make sure that you're running a variety of them so that you don't just happen to be lucky. So for today, we're going to be focusing on roots, exponents, and logarithms. And of those three, Which one do you feel least confident about? If I tell you roots, exponents, and logarithms, which one makes your brain go, oh, I don't think I remember that as well? Logarithms. So we're going to start today by reviewing our rules and also tying them together. Because the more you can tie something together, the better your brain will hold on to it. If a thought is floating by itself, very hard to get to. If it's connected to 5 other thoughts, you've got a pathway. So you were taught if I have a to the x times a to the y, you were taught a to the x to the y, you were taught a to the negative 1, you were taught a to the x over a to the y, a to the 0, So, refreshing our rules, if we are multiplying the same base, 2 different exponents, what is our simplify rule? What do we do to combine these two?
Add the exponents.
We add the exponents. So we have a to the x plus y. And this is what I mean by making connections. The logarithm is very, very simple, very, very connected. If you have the log of x plus y, I'm messing this up. If you have the log of the product, it's going to follow the same pattern. We have the product. This is just the log of x plus the log of y. And so here you had the product and it turned into multiplication. With logarithms, you have the product and it turns into addition. Product, addition, product, addition. Same rule, just a different presentation. So here we have power to a power. We have x, a to the x to the y. What happens here? How do we simplify that?
Multiply the exponents.
And so this becomes a to the x times y. In a logarithm, the same way, if we have the exponent, it becomes multiplication. This y just comes down in front, and we have y times the log base a of x. And so here, exponents became multiplication. Exponent becomes multiplication. It's the same rule. But because logarithms get isolated into their own category when we learn it, it doesn't connect as much. And so I want you to feel that connection so you don't feel like I'm having to memorize something new. I'm using what I already know on a different situation. A to the negative 1, what does that do?
Put puts it in the denominator.
It puts it in the denominator, and so we have 1 over a, and the exact same way here, you have a to the negative I. It's just 1 over a to the y power. And on logarithms, it's just going to make it into the coefficient. So we have negative log, in this case of 1. And so it just brings that negative forward. You don't necessarily have to write this one. It's just an application of those. How about division of our exponents? What does that do?
You have to subtract the exponents.
So what's going to happen over here? If our multiplication turned into adding, what's our division going to turn into? Multiplication went to adding. Division's going to go to...
I'm going to subtract.
They're going to subtract. And again, notice the denominator is what we are subtracting. How about a to the 0?
Makes it equal to 1.
Mm-hmm. And that actually ties into this one. In reality, we don't have to mess with that. It's a bad example. But if we have the log base 1, or log base a equals 1 of 1, that always equals 0. The log of 1 equals 0. Anything to the 0 power equals 1. The log of anything, the log of 1 is equal to 0. Because it's asking what question would give me the answer 1. And it's anything to the 0 power gives me 1. So we already talked about this one. How about fractions? What's another way to write a to the 1 over x? Right? Fraction exponents equal roots. Bad handwriting because it's getting low. But if I have a to the 1 over x, this is the same as the x root of a. And that one doesn't really have a logarithm equivalent. It doesn't show up. So, mostly confident with the exponent rules. I'm going to erase those for room. I'm gonna leave up the logarithm ones for a little bit longer. But the one thing that I would have you remember with logarithms more than anything else is the definition, where it comes from. So if I have y equals a to the x power, this is exponential form or an exponent. Can you write this as a logarithm? Are you comfortable going from the exponent to the log notation? That, more than anything else, is the thing that I'd like you to be comfortable with. So, it's read rhythm as log rhythm base blank. And so the base is on the bottom. And so we would read this as logarithm base A. And it's always going to come in front of the answer. So it's the log base A of y equals the original exponent. And the reverse, if I tell you the log base 5 of 7 equals, I don't know, h, can you write that as an exponent? So again, we read this as log base 5 of 7 is h. The base 5 goes on the bottom. And so the 5 will go there, and we will have 7 is equal to 5 to the h power. That ability to flip-flop in and out of the logarithm to exponential form, that is the one logarithm skill that I would take before everything else, but the rules match up with your exponent rules, and so they tend to be kind of easy to memorize. All right, that's the end of the lesson part. The rest we're going to be doing practice questions. Is there anything that I got too hand-wavy about? I don't want to make you feel like you jumped to there and they didn't make sense why. Okay. Since logarithms were less confident and we just have them fresh in our brain, we're going to start with our logarithm problems and then go into exponents. There's not that many logarithm problems. They are, at least prior to the change, kind of a rarity. I'm not sure how often they're going to show up for the new stuff. But what would this simplify to? Take a minute while the fan's running. Raise your hand if you've got an answer. I'm going to do this as the rewrite to help you understand, but in the future, you can shortcut this. And so if we set this equal to x, we can rewrite this as 5 to the 13 halves equals 5 to the x power. So what do you know about x? If these bottoms are the exact same, then the tops get to be the exact same. And so x just equals 13 halves. It looks scary because it's in the logarithm. Ooh, logarithms. No, they're just testing your familiarity. Even though that's a question 49, it's that easy. In the future, if you have the base and this number matching, this just cancels. If your base number and your log base match, they cancel out and it's just 13 over 2. So don't be over intimidated. So next one, log base x of 36 equals 2. Again, I encourage that rewrite. Rewrite this as an exponent, and it will not be so bad. What are you getting?
6.
Yeah. Remember, the base goes on the bottom, and so you're just answering the question 36 equals x squared. In general, the log questions are easier than the exponent questions. They just look unfamiliar. All right. So last two are more calculation related. I'm going to put them both up and you can answer as you go. So the first one says that if log a of x equals n and log a of y is equal to p, then find log a of x, y squared. Second question. Oh, never mind, it's the same one. It's just got different variables with it. But hey, if a question shows up twice, it means that they like it. always good to start a question without looking at the multiple choices, but after a bit, it is good to check in. Our choices are NP, 2NP, 4NP, N plus P, or 2N plus P. So whether you pay attention to the options or just tackle it straight, which part should we simplify first? What should we do first? I would deal with this first and bring it down to the front as 2 times log base A of x times y. What can we do next? Right now you should just be riffing. What can I do? Well, I can break up this multiplication into addition, and so I'm going to have 2 log A of x times y is going to be log A x plus log A y. We've split that multiplication into 2 addition problems. Here, we can match those, and so this gets replaced with n. We can match this, and this gets replaced with p. And so that's where that comes in. So at first, we can use the squared, pull down as a coefficient. We can break multiplication up into addition, and then we can replace the pieces with what they told us it was equivalent to. So, honest truth, that's as many logarithm problems as I could find, going through about 5 tests. So, have you come across any in your practice tests yet? The feedback that we've gotten from the test so far is this element of anything is fair game. You can't predict that, oh, this is definitely going to be there. This might be there, and I can't tell you if it will be for sure or not. And Manoj was talking about different people within the testing room might be taking different tests. You'll still be graded against people who took your same test, but there's no guarantee about what will be there or not. So the more you can tie it number sense into things that you're familiar with, like the exponents, the better off you are. And the first 2 were very simple and just able to do a change of base, the anti-log from log, turning it back into exponents, and then find the answer. This one, you had to truly use the rules, and as long as you know those rules, the substitution is pretty user-friendly. So, in general, exponents show up a lot more, and they tend to be a little bit more complicated, a little bit wordier. So, they want you to simplify 2 a to the negative 1 square root of b all to the 4th power over a b to the negative 3. We also have negative 2 x to the 5th y squared all to the 4th power. So both of these fall in the middle of a test, and they're straight simplification. You're trying to get rid of roots, you're trying to get rid of negatives, rewrite the expression. I'm going to give you 2 minutes. All right. First one. What would you do first? There's not necessarily a right or a wrong answer, but just how your brain tackles it. What would you do first?
Distribute the exponent.
Distribute the exponent? I agree. That's probably the safest one. So, on these, I always glance at the multiple choice to know whether they're leaving the numbers as 2 to an exponent or whether they multiply them out. In this case, they are multiplying them out. So 2 to the 4th power is 2 times 2 times 2 times 2, or 4 squared, we've got 16. We have a to the negative 4th. How about the b squared? What does that simplify to? B squared to the 4th, or b square root to the 4th power.
B squared?
Yes.
Or b to the power 2?
It helps you to look at this b square root and think of it as b to the 1/2. 1/2 times 4 can make it easier to see that b squared, that 2. And so if that helps you, go for it. But this becomes b squared. And then we have a b to the negative 3. What next?
Subtract the exponents.
Subtract the exponents? Okay. How do you do that? These ones are always kind of a brain thing. Everybody sees them a little bit differently. I see them as move the negative ones. That's how my brain functions. And so a to the negative fourth, a to the positive 1, I want to move this down, is how my brain sees that, to get it to the positives. And so this becomes a to the fourth, because the negative makes it move. It's always going to switch sign when it switches the top or bottom of fraction. And so we become positive a to the fifth. The same way we have b to the negative 3, you could see that as subtracting and have 2 minus negative 3, or you can see it as moving it and then it becomes b to the 2 plus 3. But either way, we're going to have b to the fifth up above. And the 16 hangs out. Anything I got too hand wavy on? So if you're more algorithmic, again, you could have seen this as a to the 1 minus negative 4. But I'm more of a change the sign and then combine person. All right. Key question on this one, the fundamental mistake. When I distribute the exponent, same as last problem, it happens to be a 4 again. Not a guarantee, just a coincidence. What is my number out front going to be? Yes. Whether you see this as to the 4th power this way, or you see that negative going to the 4th on its own, either one is okay, but you need to recognize, oh, negative to a even power, it's going to become positive 16. And so don't forget to cancel out that negative sign. Everything else super easy. X to the 5 times 4 is 20. Y to the 2 times 4 is 8. So, again, straight calculation problems. Be familiar with the rules, but they're pretty straightforward. All right. This one is more of a logic solving problem. We have A, B, and C are consecutive integers. Two to the A times 2 to the B times 2 to the C equals 512. The question is 2 to the A plus 2 to the B plus 2 to the C equals, oh, sorry, my exponent got low. Since we're running low on time, 2 to the what equals 512. How many times do we have to multiply 2 by itself to get to 512? Worst case scenario, start with 512 in your calculator, start dividing by 2 and see how many times you do it. Or you can run test numbers, 2 to the 8th, 2 to the 10th. What does it take to get to 512? I don't have a calculator, so I'm waiting on you to tell me.
Nine.
2 to the 9. I knew it was somewhere in there. So we want 9. So the next question is A, B, and C. What are 3 consecutive integers that add up to 9? One of the ways to think about that is 9 could be 3 plus 3 plus 3. And so to make the consecutive integers, take 1 from this one and give it to the next one. And so now we have 2 plus 3 plus 4 would equal 9. And so now we have 2 squared plus 2 to the 3rd plus 2 to the 4th. What does that equal?
$28.
And that is our answer. So that one is a 50 on the old test, so relatively near the end. You can see it's got a lot of moving pieces. You've got to understand, hey, these 3 things would add together. We've got to understand how to get to 512. We can find those consecutive integers and then essentially run it through the calculation to get the answer. Burying answers inside another calculation, that one's a pretty common one. All right, one last one. This is a style that they're rather fond of. And so if you get how to change it, they're not bad, but they're a little tricksy. So, again, back to the original question. Not necessarily what is the answer, but what is the first step in finding the answer? What is the key to these problems? We're running out of time, so if you don't know, I'm going to tell you. Does anybody know? Okay. The key to these problems is a common base. We want to get the same number on the bottom so we can restrict our comparison to just the top. And so 9 can be written as a base of 3. This one's going to stay the same as 3x plus 1. But this 9 we can turn into 3 squared. And we already talked about exponents to a power are just multiplied. And so this becomes 3x plus 1 equals 3 to the 2x minus 4. And so this is what you're solving. It just turned into an Algebra 1 problem. The same way on the next one, 4 and 8 can both be written as base 2. And so this becomes 2 squared to the 1 minus a, and 2 to the third, 2a plus 1. And we have, oh sorry, my a is starting to look like a 9 there. So we have 2 minus 2a equals 6a plus 3. Because we're just comparing those exponents there. And so when they're asking you to solve a problem where you've got variables in both of the exponents, try to get them into a common base and solve from there. Because once you get there, Algebra 1, you're great. But if you can do that change of base, it makes your life so much easier. All right, with that, we are out of time. Have an excellent week. We'll be back in a couple weeks.